Welcome, this is Dr. Plague, and in this video I have a few points I want to touch on. I want to provide an introduction to some upcoming videos on homemade CPU designs and such. I want to talk about who inspired me to start designing homemade CPUs. I want to explain what I will be using as building blocks for these homemade CPUs. And I want to go to the bench and demonstrate some of the characteristics of the ICs I'm selecting. We'll do all that right after this. So the next few videos that I plan on creating will concentrate on a few CPU designs. Then I'll probably start looking at some homemade video circuits since we need to connect our CPUs up to something, right? I want to start out with some very simple CPU designs and use those as building blocks for more complex designs. The first CPU that I'll be making, which I'll call the Plague Mark I, will be so simple that we really can't even call it a CPU per se. But I need to start somewhere. This first CPU will be so simple and basic that I should be able to design and build it all in one video. There may be a second video on it just to experiment more with it, but the design will be very simple. Then we'll move on to the Plague Mark II, which will add a lot more functionality. Then the Plague Mark III, etc. All these CPUs will be programmable to some extent, and they will execute code stored in a flash memory chip, which is the reason I created previous videos on making a homemade flash memory programmer. Starting out, we'll only need to program a few bytes of code into the flash chips, but I will get to the point where we need to load larger files into the flash chips. So at that point, I will take a break and go back to the Flash Memory Programmer series to modify the Flash Programmer for the ability to program larger files. Now, these first few designs of CPUs will be more geared towards an audience of viewers that have no idea where to start with creating their own CPUs. But they may also be interesting to those who are more experienced, as you will get to see another perspective for homemade CPUs. So, why am I making these homemade CPUs? To be honest, they're not going to be very useful, but they will be a lot of fun to design. And after all, isn't that the whole reason we all got into the hobby of electronics? To have fun? Also, another key point is that it can be a good learning experience to see firsthand how logic can be combined to perform certain tasks. And it will certainly provide us with some good digital circuit debugging experience. Now, where did I get my inspiration from for these homemade CPUs? Well, ever since my early days with 8-bit computers, I've always been interested in how a CPU worked. And I worked on creating all kinds of simple computer logic circuits. It all stemmed from a kit that I got back in the 1980s from Radio Shack. I believe it was the 160-in-1 Electronics Project Kit. But it wasn't until the late 90s or so when I got a glimpse of a project that a man named Victor T. Toth was working on. He created what he called Victor's Amazing 4-bit Processor. He made this processor out of 74 series logic, and he built it on perf boards. You can go check out his website if you're interested. As of the date I made this video, he still has his amazing 4-bit processor on his website. You can find his website by searching for Victor T. Toth. So, I did not copy his design in any way, but it was his project that really inspired me to start creating my own processors. What I did was kind of like a clean room design. I read about his project, but didn't study it in depth, and then I went off and designed some of my own processors without referring back to another design. But without Victor, I may never have came up with some of these designs to begin with. So please help give Victor some credit for some of the awesome homemade CPU designs that we see today. One of the processors that I'll be developing in this video series will be based off of a processor design that I created over 20 years ago. It was a 16-bit processor. However, I will be simplifying it into an 8-bit processor to make it easier to breadboard up. These are processors that I have never built or tested in any way other than in a simulation, so we'll get to see firsthand if any of them actually work. I suspect that I'll need to make some adjustments along the way. Now, what am I going to use as the main building blocks for these homemade CPUs? There are many choices, but perhaps the most common choices are to use 74 series logic ICs, or program the design into some type of a programmable logic chip using VHDL or Verilog. I'm going to choose the former of the two. I'll be making my CPUs out of 74 series logic chips. It just sounds like a lot more fun rather than making videos on coding up the internal workings of CPUs. Not only that, but I believe it will be easier for my viewers to catch on and develop their own CPUs. I have designed CPUs inside of FPGAs, and in fact, I was required to design an FPGA CPU way back in college when I was working on my engineering degree. Part of that assignment required the homemade CPU to execute a fast Fourier transform. Fun times. And here are a couple of the textbooks that we used back in college. Here's a chapter on designing a pipelined RISC microprocessor. So maybe we can get into some of that in future videos. But for now, I just want to have some fun with the most hobbyist-friendly builds by using 74 series logic. And what could be more fun than to build a giant circuit out of ICs and wires and have the ability to watch that beast come to life and execute our own code? So, some of you may be thinking that building a CPU with all kinds of 74 series logic will be very complex and may require all kinds of electrical engineering knowledge. Well, to be honest, in my opinion, I don't think you need to know a whole lot about electrical engineering to get started in designing some simple CPUs. Just a basic knowledge of electronics is all you should need. Also, you should have the ability to understand basic logic, such as knowing that a 2-input AND gate will only produce a high on its output when both of its inputs are high. Let's look at it this way. Suppose I want to make a CPU out of Legos, and I have some building blocks here. We can put them together to make a very crude-looking CPU or IC chip. This doesn't require much knowledge, just some simple imagination. That will be the same with 74 series logic. If you're not familiar with 74 series logic, you can think of each chip as a beast. The beast will usually have some type of logic function that it will perform. The input pins of the beast will each be one of its mouths, and a gate within the beast will be its belly. Now, bear in mind that each beast can have not only multiple mouths, but also multiple bellies. When you have signals that you want to send to the beast, you feed them into its mouths, and then it will go from there into its belly to be digested. We can consider the time that the belly takes to digest the signal to be its propagation delay. And after the signal is digested, the belly will shoot it out of the beast's...
You are disgusting. You always have such barbaric and gross ways to describe things.
But I'm just...
I want you to be a little more graceful with the way you describe things.
But...
Okay?
Oh, all right. So anyway, you can look up how different logic chips work by looking at their data sheets. In fact, I have a couple very useful books right here, which have all kinds of 54 and 74 series logic chip data sheets, which can be easily looked up. This book has TTL logic in it, such as LS chips, and this one has CMOS logic, such as HC and HCT. These are very old books from the mid-'80s. This one is from 1985, and this one is from 1984. And if you can find one of these types of books for sale, I would recommend getting your own if you don't already have one. It can be very handy to have a good hard copy of all these data sheets. Also, be careful when using 74 series logic, as they don't all conform to a standard pinout. Look at the 74 Series 01 chip. The SN7401 and SN74LS01 have their inputs for their first gate on pins 2 and 3, with the output on pin 1. But the SN74H01 has its inputs on pins 1 and 2, with the output on pin 3. Also, don't just assume all the 74 Series chips have their power pins in the corners. Look at this SN74LS91 chip. Its power pins are more towards the center. Just make sure you're checking data sheets for pinouts is all I'm saying. So, we know that I have selected 74 Series logic for my building blocks. But what family of 74 Series logic will I be using? There are many different families of 74 Series logic, but perhaps the most common are LS, HC, and HCT. I'll be choosing primarily chips from the HCT family. If you are unfamiliar with 74 Series logic, you can tell what the family is by looking at the letters between the 74 and the identifying number for the logic. For example, a 7400 is a quad 2-input NAND gate. LS versions will be 74LS00, HC versions will be 74HC00, etc. If I'm just talking about a particular logic type and I don't care about the family, I'll just place an apostrophe after the 74, such as 74'00. Now, probably the most commonly used 74 Series logic family for hobbyists is the LS family. So, why am I choosing the HCT family? Well, the primary reason is due to the low current consumption of HCT ICs compared to LS ICs. LS ICs can be current hogs. And since I'll be creating some designs with a high number of ICs, I'll really want to keep the current consumption low so we don't need a big, beefy power supply. The reason I'm not choosing to use HC versions is due to their incompatibility with LS versions. You see, LS versions are typically not guaranteed to output anything higher than about 2.7 volts, but HC versions typically require around 3.15 volts to be guaranteed to detect a high. These specs are typical. There can be exceptions. HCT versions were designed to eliminate this incompatibility, but of course it all comes with a price, but I won't get into that. Why do I care about compatibility? Well, while most of my new 74 Series logic ICs that I purchase are HCT, I do have a large selection of older LS ICs in my collection. So, there may be the occasion where I may want to test out a particular 74 Series logic chip, but I don't have any in the HCT family. There's a good chance I'll have an LS version of it. And since LS and HCT versions play nicely together, I can use the LS version until I am able to replace it with an HCT version. Now, LS chips can have some advantages over HCTs. For example, you could directly drive LEDs with them without the need for current-limiting resistors, since they have a built-in resistance that helps limit the current. I'll show an example of driving an LED with a 74LS04 hex inverter. So here's a 74LS04 with all its inputs grounded. I'll first measure an output voltage, and I'm getting about 4.3 volts. Next, I'll add in an LED to an output and connect a meter up to it to measure current. It lights up fine, and we can see it only delivers about 13.4 milliamps to the LED. And the voltage drop across the LED is about 2 volts. Don't try this with an HCT version. Now, I still wouldn't recommend doing this even with the LS versions. Let's do the math. If we have 4.3 volts with no load, then we can say the drop across the transistor is about 0.7 volts. So the 5-volt supply minus about a 0.7 volt drop across the transistor minus 2 volts across the LED leaves us with 2.3 volts across the resistor. And if there is 13.4 milliamps, then we have about 172 ohms for the resistor, which is a little higher than the schematic, which claims to have 120 ohms here. Let's calculate this with other possible values. Let's start with 5 volts and say we have an LED that takes 1.4 volts. And let's say there is about a 0.7 volt diode drop across the transistor, and with 120 ohms, we get about 24 milliamps, which can be a little excessive for an LED. And besides, these LS chips aren't really designed to be driving LEDs. So, if you are driving LEDs with an LS chip, I would still recommend using current-limiting resistors. Now, there are 2 primary types of power consumption that logic chips will have. There is power consumption from quiescent current, that is, current when the IC is sitting dormant. It's powered up, but the inputs aren't changing. Then there is power consumption due to frequency-dependent current, which increases as the frequency of operation increases. HCT chips will typically have close to 0 quiescent current draw, which well outperforms LS chips. Let's test this out. I have all the inputs on the LS chip connected to ground. Let's connect the meter to the power supply return path to measure the quiescent current on the LS chip. And we get about 1.58 milliamps. And if we replace that IC with an identical HCT hex inverter chip, the 74HCT04, we get no noticeable quiescent current. We'll try this same test, only this time I'll connect all the inputs to VCC. For the LS chip, I measure about 4.33 milliamps. And for the HCT chip, I measure pretty much nothing. And just to show you that this IC is powered up, I've grounded one of the inputs and I'll measure a high on the output pin, about 4.99 volts. Next, I'm injecting a high into the first input and connecting each output to the next input, so all the outputs alternate. And for the LS chip, I get about 2.88 milliamps. And I'll verify that the last output is a high, and it is. Next, I'll try the same with an HCT chip, and again, no noticeable quiescent current. And the last output measures a high. Let's connect up a signal source to see the frequency-dependent current. I'll connect a waveform generator to the first input on the LS chip. And I'll connect a scope probe to the last output so we can verify that it toggles. This will make sure that the signal is propagating through all the inverters. I'll apply power, and we get about 2.9 milliamps. The waveform generator is set up to send out a 5 MHz square wave. Let's turn it on. And we can see that the current jumped up to about 4.5 milliamps. Let's try this with the HCT chip. And again, it starts out with no noticeable quiescent current. Then, after turning on the 5 MHz square wave, we get about 4 milliamps. It's close to the LS chip, but still below it. So, in all cases, I've measured less current draw with the HCT chip than I did with the LS chip. Keep in mind that this is only one type of logic chip, the hex inverter. To be fair, we would need to test all types of logic chips. But the results of this test are promising, and helps to reinforce my decision to use mostly HCTs in my designs. They also have other advantages, such as a much higher fan-out capability. If you're not familiar with fan-out, it just means how many other inputs are being driven by a particular output. Let's do a quick test to see how LS chips compare to HCT when it comes to output current. What I've done here is connected all the inputs of the LS version of the hex inverter to ground, so the outputs should be high. I'm going to connect 5 volts from channel 2 of my Instack power supply to power and ground. Then I'll connect the output of the first inverter, which is pin 2, to channel 1 of my Instack power supply. I have channel 1 configured as an electronic load in constant current mode, meaning that I can pull a particular value of current from the LS chip's output pin. And if I power up the circuit with channel 2, you can see that channel 1 shows us how much voltage is on the output pin, and it'll climb to just over 4 volts. Next, I'll turn on channel 1, which is currently set to draw 0 milliamps from the output pin. And I can turn that up to 1 milliamp, 2 milliamps, and as we keep climbing, notice how the voltage drops significantly. I'll go up to 10 milliamps. And look at how we now only have just over 2 volts on the output. Ouch! We've just tanked that output voltage with only 10 milliamps. Now let's try the HCT version. Notice how the output is right up to about 5 volts. Okay, let's do this. Let's start cranking up the milliamps. And notice that when I get to 10 milliamps, we still have almost 4.5 volts on the output. Fantastic! Get it? Fantastic? Anyway, the HCT can support a much higher fan out, not only because it can drive more current at a higher voltage, but also because HCT inputs have a much higher input impedance than LS versions. But the HCT fan out is not unlimited. We still have capacitive loading to deal with. Now, there are other tests we could perform, such as rise and fall times versus current draw and such, but I'll leave that to you if you want to test any of that out. One thing we want to be careful with is the operating speed of these devices and propagation delays. But the speeds that I'll be running these homemade CPUs at won't be very high. But you always want to check the datasheets. Speeds will differ between different LS and HCT parts. Well, I think I've covered enough for today. I'll start working on the CPU videos and we'll dig into this more in future videos. Thanks for watching, and I'll see you next time, right here on Dr. Play.